Welcome, everyone. Let's get started on mastering how we securely control large language model access within Snowflake Cortex. Hello and welcome. Today, we are diving deep into a critical governance feature in Snowflake Cortex, controlling AI model access. As organizations adopt AI, you cannot just leave the gates wide open. You need stringent control. This is exactly where the Cortex model's AllowList parameter comes into play. Think of this parameter as your primary security checkpoint. It is an account-level setting that explicitly dictates which large language models, or LLMs, your users can access when executing Cortex AI functions. We will explore what this is, why it is absolutely essential, and how it serves as a simple but broad control mechanism to effortlessly enforce your organization's governance rules across your entire Snowflake account. Let's take a look at the visual breakdown of Snowflake Cortex Access Control. As you can see on the screen, when a user interacts with Snowflake Cortex, their request immediately hits an access control checkpoint. From here, Snowflake utilizes two distinct but complementary mechanisms. First, we have the Cortex model's AllowList, branching off to the top right, which provides an account-wide, broad level of security control. Below that, we have role-based access control, or RBC, which allows for highly fine-grained user control. Throughout this training, we will focus primarily on the AllowList, but we will also cover exactly how it integrates seamlessly with RBC to provide an unbreakable security posture. Why do we even need to control model access? Why not let data scientists and business analysts use whatever model they want? The answer boils down to three enterprise pillars: compliance, cost, and complexity. First, compliance. Unrestricted access might allow highly sensitive data to be processed by a third-party model that hasn't been vetted or approved by your InfoSec team. Second, cost management. Different models consume drastically different amounts of compute credits. A massive 405 billion parameter model costs significantly more per token than a smaller 8 billion parameter model. By restricting access, you automatically prevent accidental budget overruns. Finally, simplification. By only surfacing the approved models, you reduce confusion for your end users, streamlining their daily workflows. This mind map perfectly illustrates the core motivations behind restricting model access in your data cloud. At the center is our main goal: controlling access. Branching out, you see the three main drivers. On the top right, compliance is key, ensuring data privacy and adhering to strict regulatory rules. On the bottom right, cost management is critical, as we need to proactively govern token usage and the associated compute credits to avoid end-of-month billing surprises. Finally, on the left, we have governance, which ensures engineering standardization and robust security across your enterprise. By leveraging the AllowList, you effectively address all these branches simultaneously. Now let's cover the foundational basics of how this parameter actually functions in practice. The Cortex model's AllowList is strictly an account-level parameter. This means you absolutely cannot set it at the individual user or session level. Because of its broad, sweeping impact, only an administrator possessing the account admin role has the authority to modify it. When configuring this parameter, you have three distinct operational options. You can set it to all, which is the default setting, granting access to every available model. You can set it to none, which completely shuts down account-wide model access. Or, most commonly for strict enterprise governance, you can provide a comma-separated list of specific model names, such as Mistral, Large 2, and Llama 3.1-70B. This state diagram walks you through the configuration hierarchy and its ultimate outcomes. It starts at the top with the account admin, the only role authorized to execute the alter account command to modify this powerful parameter. From there, the configuration logically forks into three potential states. State 1 is all, meaning every model is globally available. State 2 is none, meaning no models are available by default across the board. State 3 represents a targeted approach, where you provide a specific, curated list of models. The final output boxes show exactly what the end users experience based on the administrator's chosen configuration state. Let's look at the exact SQL syntax for configuring the AllowList in your environment. As the account admin, you will use the standard alter account command. If you want to restrict your environment to just two highly efficient models, you would execute alter account set Cortex models AllowList equals, and then inside single quotes, Mistral, Large 2, Llama 3.1-70B. It truly is that simple to implement. If a user tries to access a model not on this specific list, Snowflake will securely block the request. Alternatively, if your organization requires strict, granular control where every single user's access must be explicitly granted, you would execute alter account set Cortex models allow list equals none. This establishes a pristine zero-trust baseline. This sequence diagram clearly illustrates the practical effect of the allow list parameter in real time. First, the account admin sets the allow list to only permit the Mistral large 2 model. Next, a data analyst attempts to run the AI complete function using that exact approved model. Because it matches the allow list, Snowflake processes it and returns a success. However, in the very next step, the same analyst attempts to use the Llama 3.1-405B model. Since this model was completely omitted from the administrator's allow list, Snowflake immediately intercepts the request and returns an error, preventing the unauthorized usage and protecting your compute budget. Now for the technical deep dive, how does Snowflake actually evaluate an execution request under the hood? When a Cortex AI function like AI complete is called, Snowflake initiates a highly specific resolution sequence. First, it looks for a matching model object natively in the Snowflake.model schema. If it finds this object, it strictly applies role-based access control, or RBC, to determine if the user's role has the proper permission. But what exactly happens if no model object is found? That is precisely when Snowflake falls back to the account-level allow list. It checks the string provided in the function call against the Cortex model's allow list parameter. If the model name is in the list, the execution proceeds. If not, it fails. Follow the logical flowchart on the screen to understand the exact decision tree Snowflake uses. At the top, the user calls an AI function. The system immediately asks, is the model object present in the Snowflake.model schema? If yes, it routes left to meticulously evaluate RBC. If the user has access, the model executes. If not, it's blocked. But if the object is not in the schema, the system routes right and checks our Cortex model's allow list. If the model is listed there, execution is granted. If it is missing from both the RBC grants and the allow list, the request is securely blocked. It is an elegant, multi-layered defense mechanism. The true architectural power of Snowflake Cortex governance lies in combining the broad stroke of the allow list with the surgical precision of RBC. Imagine you want every employee to have access to a fast, cost-effective model for basic daily tasks, but you want to reserve a highly capable, expensive model strictly for your senior data scientists. You can set the Cortex model's allow list to include only the basic model. Then, using RBC, you grant the application role for the advanced model exclusively to the senior data scientist role. Because Snowflake checks RBC first, the data scientists bypass the allow list restriction for that specific model, while everyone else remains safely contained within the baseline allow list. This diagram visually details the combined architecture. In the top account level box, the allow list is set to Mistral 7B, making it safely available to the public role, meaning everyone gets basic access. In the bottom RBAC level box, we see a specific high-tier role, the data scientist, being explicitly granted an application role for the much larger Llama 3.1-405B model. These two independent rules merge perfectly at the combined access node. Regular users only see the basic model, while the data scientist enjoys access to both. This hybrid approach beautifully optimizes both cost and capability without ever sacrificing strict data governance. Let's contextualize this with a real-world use case. Consider a highly regulated healthcare provider analyzing patient feedback. They have strict compliance requirements and have determined that protected health information, or PHI, can only be processed by specific open-source models that run entirely within their trusted Snowflake boundary, preventing data from being sent to external third-party LLMs. To enforce this instantly across thousands of concurrent users, the account admin sets the Cortex model's allow list to exclusively allow Llama 3.1-8B. Now, even if a junior analyst mistakenly writes code requesting an external proprietary model, the Snowflake platform intercepts and blocks it immediately. The allow list acts as an automated compliance guardrail, ensuring no PHI leaks to unapproved endpoints. In this sequence diagram for our healthcare scenario, the analyst first attempts to send PHI data to an unapproved model. Snowflake Cortex instantly checks the allow list, sees the model is prohibited, and securely returns a blocked message. Correcting their code, the analyst then requests Llama 3.1-8B, which is the approved model listed securely on the allow list. Cortex allows this authorized request to pass, routing the data securely to the local model, processing the insights, and delivering the results safely back to the analyst. This proves exactly how the LLMs physically prevents massive compliance breaches before they can even occur. To summarize our session, the Cortex model's LLMs is your fastest, most effective tool for establishing baseline security and cost control for AI features in Snowflake. Whether you are setting up a strict zero-trust environment with none or providing a curated list of approved models, it ensures absolute, uncompromised governance. Remember to integrate this with RBC for granular entitlements, and always monitor your token consumption using the Cortex function's usage history view. Thank you for joining this deep dive. I invite you to like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides to accelerate your career. Our final diagram outlines your ongoing operational workflow for success. You start on the left by securely setting your baseline using the LLMs. Move to the next step by defining any specific RBC exceptions for your power users. Then, continuously monitor your environment using Snowflake's usage history views. When you diligently combine these three steps, the result is the golden node on the right, optimized and secure AI. Be sure to check out quicktechie.com for more in-depth architectural patterns. Thanks for watching and happy building!